You have built a three-dimensional reservoir model, estimated the oil in place, booked the reserves, and secured $8 billion in project finance, and still not a single barrel has reached the surface. Cased it, cemented it, logged it, cored it, and tested it. Everything up to this point has been preparation, geology, geophysics, engineering, finance. But the moment you actually begin extracting oil, the moment you turn a discovery into production, you enter an entirely different problem set, one that operates 24 hours a day, 365 days a year in some of the most hostile environments on Earth. The ground to a continuous, reliable, safe production system. It is about the engineering that nobody sees, the thousands of meters underground, producing for decades without human intervention. It is about flow assurance, the battle against choke $1 billion well in hours. And it is about the moment of first oil, when everything you have designed, built, and invested finally begins to pay you back. After the drilling rig leaves, the well is just a hole, a steel-lined, cement-sealed hole. It does not produce. It cannot produce. Formation pressure also seals the reservoir off from the wellbore. To begin production, you must deliberately breach that barrier in a controlled, precisely targeted operation called a completion. The first step, and the most violent, is perforating. A perforating gun is lowered into the well on wireline or coiled tubing. It is a steel cylinder loaded with shaped charges, explosive devices that focus their detonation energy into a high-velocity jet. 7 kilometers per second, punches through the steel casing, through the cement sheath, and deep into the reservoir rock. Less than 2 centimeters in diameter, but it is the only pathway through which oil will enter the wellbore for the next 20 to 30 years. Through the production tubing, not through the wide annulus of the casing, and reaches the surface as a high-velocity, controlled stream. Once the zone is perforated, the completion engineer must decide how to configure the well for production. Majority of vertical and deviated wells is the cased hole, tubing, and packer completion. A packer is a mechanical device that seals the annular space between the production tubing and the casing. It forces all produced fluid to travel up through the tubing rather than through the wider, uncontrolled annulus. This is critical for 3 reasons. First, it protects the casing from corrosive formation fluids. Second, it provides well control. The valves at the surface, and the packer prevents formation pressure from reaching the casing. Gas can be injected into the annulus to lighten the fluid column, or an electrical submersible pump can be installed at the bottom of the tubing. The production tubing itself is smaller than the casing, typically 3.5 to 5 inches in diameter. Up the wellbore and prevents the accumulation of water or condensate at the bottom of the well. A well that cannot lift its own liquids will eventually open hole completion, no perforating. Producing interval is left as bare rock. Simple, low cost, but provides no zonal isolation. Used in competent, naturally fractured formations like carbonates. Gravel pack completion. In unconsolidated sandstone reservoirs, the formation sand would flow into the wellbore along with the oil, eroding equipment and filling the well. A gravel pack places specially sized sand or ceramic particles between the formation, holding the formation sand in place. And in weak, unconsolidated formations, common in of the Middle East, sand production is the completion engineer's nightmare. Velocity acts like a sandblaster, eroding tubing, valves, and surface equipment. Left uncontrolled, sand can destroy a multi-million-dollar well in weeks. The solution is a gravel pack, essentially a highly engineered filter. Carefully sized gravel, typically 20 to 40 mesh, is pumped into the annular space between the formation and the sand control screen. The gravel bridges the formation sand, holding it in place. The screen prevents the gravel from entering the wellbore. and the oil, free of sand, flows cleanly to the surface. A properly designed gravel pack can last the entire productive life of the well, requiring an expensive workover or a sidetrack well. Shutoff. Above it, the upper master valve. Redundancy for safety-critical applications. The production wing valve diverts flow to the production line. The kill wing valve provides access for pumping fluids into the well to kill it in an emergency for wireline intervention. And the choke, typically an adjustable bean choke, controls the flow rate and creates back pressure on the reservoir. Pressure gauges flank the tree, displaying tubing pressure on one side and casing pressure on the other. Automatically in an emergency shutdown completes the assembly. The Christmas tree, named because its vertical arrangement of valves and fittings resembles a decorated tree, is the primary pressure control system at the surface. It is built to contain the full shut-in pressure of the reservoir. On a high-pressure, high-temperature well, a so-called HPHT well, that can mean containing pressures exceeding 15,000 pounds per square inch and temperatures above 300 degrees Fahrenheit. Producing life of the well, 20, 30, even 50 years, without leaking, without failing, without a single unplanned shutdown. The component names are not decorative. They survive from the early days of the industry, when roughnecks named equipment for what it did, and the names stuck. The primary and secondary barriers. In any well control event, a pressure spike, a leak, an emergency, closing the master valves isolates the well from the surface. They are designed to cut through wireline or coiled tubing if necessary. They are tested regularly. They are never used for routine flow control. That is the choke's job. The choke is the only valve on the tree designed for throttling. It is a precision machined orifice, a bean, that restricts the flow area and creates a controlled pressure drop. The choke setting determines the flow rate, the wellhead pressure, and, critically, the drawdown applied to the reservoir. Excessive drawdown can cause sand production, gas coning, or water breakthrough. Insufficient drawdown and the well produces below its capacity. The choke operator balances these forces every shift. Subsea tree, an entirely different design. The tree sits on the ocean floor, connected to the platform by flow lines and control umbilicals. It is operated remotely through hydraulic and electrical lines running from the surface. Everything that would be a manual valve on a surface tree becomes a hydraulically actuated valve on a subsea tree. A subsea tree can cost $5 to $10 million, and 20 times that if something goes wrong and requires an intervention by a remotely operated vehicle or a drilling rig. On an offshore platform, the tree is bolted to the wellhead on the production deck, accessible to operators. Developments where the reservoir is kilometers below the seabed in 1,000 meters or more of water. The tree sits on the ocean floor. It is installed by a drilling rig. It is operated remotely through umbilicals carrying hydraulic fluid, electrical power, and communication signals from the host platform kilometers away. A subsea tree must function without human intervention for its entire design life, often 25 years or more. Every valve actuation, every pressure reading, every choke adjustment, all done remotely. If something breaks, you do not send a technician. You send a remotely operated vehicle, an ROV. And if the ROV cannot fix it, you mobilize a drilling rig at a day rate that can exceed $500,000. The animation follows the flow line to the production manifold, a collection point where flow from multiple wells is combined, and then into the first stage separator. The separator is a large horizontal pressure vessel. Inside, the fluid slows down dramatically. Bottom. The oil occupies the middle layer. 3 separate outlet streams emerge: gas from the top, oil from the middle, water from the bottom. What arrives at the surface is not a barrel of clean crude oil. It is a turbulent, corrosive 3-phase mixture: oil, gas, water, and whatever else the reservoir decided to send along. Formation sand, corrosion products, emulsions, oil and water mixed so intimately that they refuse to separate. The first job of the surface production system is to split this stream into its components. The workhorse of separation is the 3-phase separator, a horizontal pressure vessel, typically 10 to 20 meters long and 3 to 4 meters in diameter. The incoming fluid enters at one end and is immediately slowed by a deflector plate. The reduction in velocity from meters per second in the flow line to centimeters per minute in the separator is the primary separation mechanism. Given enough time, gravity will do the work. Gas, the lightest phase, rises to the top and is drawn off through a mist extractor that captures entrained liquid droplets. Water, the heaviest phase, settles to the bottom and is removed through a water leg and out through the oil outlet. 2 to 5 minutes determines how clean the separation will be. The separated oil stream enters a heater treater, a vessel that heats the oil to break emulsions and drive off remaining water. Electrostatic treaters use high-voltage electrodes to coalesce water droplets, accelerating separation. The specification for pipeline quality crude is typically less than 0.5% basic sediment and water, BS&W. Exceeding that limit can cause pipeline operators to reject the shipment and impose penalties. The water, often hundreds of thousands of barrels per day from a large field, cannot simply be discharged. It must be treated. Produced water contains residual oil, dissolved hydrocarbons, formation minerals, and sometimes naturally occurring radioactive material. Water treatment facilities remove these contaminants through hydrocyclones, flotation units, and filtration until the water is clean enough for reinjection into the reservoir, where it serves as a pressure maintenance mechanism or for disposal into a dedicated injection well. And the gas, depending on the field, either fuels the platform's generators, is re-injected into the reservoir for pressure maintenance or later recovery, or is compressed and exported through a dedicated gas pipeline. In some fields, particularly in remote locations without gas infrastructure, the gas is flared, burned at the top of a flare boom. Flaring is increasingly regulated, taxed, and restricted, but in the absence of a commercial route for the gas, it remains the default safety mech. Flow assurance is the engineering discipline of keeping the produced fluids moving from the reservoir to the sales point. It sounds simple. It is anything but. The hostile conditions inside a production flow line, high pressure, low temperature, a mixture of oil, gas, and water, create a chemical environment in which solids can form, deposit, and eventually block the flow entirely. A plugged flow line in deep water can stop production from an entire field, with losses measured in millions of dollars per day. The most feared flow assurance problem, and the most dangerous, is gas hydrates. Hydrates are ice-like crystalline solids in which water molecules form a cage structure around gas molecules, typically methane, ethane, or propane. They form at high pressure and low temperature, precisely the conditions found in deep water flow lines and during well shut-ins. A hydrate plug can form in hours, and once formed, it can be extraordinarily difficult to remove. The remediation of a hydrate blockage, carefully depressurizing the flow line, sometimes over weeks, to melt the plug without dislodging it as a high-velocity projectile, is among the most dangerous and expensive operations in the industry. Thermodynamic inhibition, injecting methanol or monoethylene glycol, MEG, into the flow line. The inhibitor shifts the hydrate formation curve to low, essentially making it harder for hydrates to form. The inhibitor is recovered at the host facility, regenerated, and re-injected. For a large deep water field, the cost of MEG regeneration alone can run into tens of millions of dollars in capital expenditure. Insulation and heating, keeping the fluid temperature above the hydrate formation temperature through passive insulation, pipe-in-pipe flow lines with vacuum insulation panels, or active heating, using electrical heating cables integrated into the flow line. Electrically trace-heated flow lines are increasingly common in long-distance deep-water tiebacks, where the cool-down time after a shut-in would otherwise be too short to safely restart production. Wax, paraffin, is a different problem with the same result. As crude oil cools, the heavier paraffinic components begin to crystallize and deposit on the pipe wall. The deposit grows, slowly at first, then faster as it narrows the flow area and increases the pressure drop. Wax deposition reduces throughput, requires periodic pigging, running a cleaning device through the pipeline, and in severe cases can plug the line entirely. Asphaltenes are the heaviest, most complex, and least understood fraction of crude oil. They are not dissolved in the oil. They are suspended as colloidal particles stabilized by resins. When the equilibrium is disturbed, by pressure changes, by gas injection, by the mixing of incompatible crudes, the asphaltenes flocculate and precipitate. They deposit in the wellbore, in the tubing, in the flow line, and in the separator. Removing asphaltene deposits typically requires aromatic solvents and mechanical cleaning, both expensive, both disruptive, neither guaranteed to work. And scale, calcium carbonate, barium sulfate, strontium sulfate, precipitates from produced water when pressure drops and dissolved gases come out of solution. Scale can coat the inside of production tubing like concrete, reducing the effective diameter and choking off production. Scale inhibition relies on chemical injection, phosphonates polymers dosed continuously into the produced fluid. If scale forms before the inhibitor reaches it, you are already too late. 4 artificial lift systems are illustrated in sequence. Electrical submersible pump, ESP, a multi-stage centrifugal pump driven by an electric motor installed at the bottom of the production tubing. The animation shows the pump stages, rotating impellers and stationary diffusers, adding pressure energy to the fluid, boosting it to the surface. An ESP can lift enormous volumes, up to 60,000 barrels per day, but it is sensitive to gas, to sand, and to high temperatures. The motor relies on produced fluid flowing past it for cooling. If flow stops and the motor is not shut down immediately, it will fail within minutes. Gas lift. High-pressure gas is injected into the annulus between the tubing and casing. It enters the production tubing through gas lift valves. Precisely calibrated pressure-operated valves spaced at intervals along the tubing string. The injected gas lightens the fluid column, reducing the hydrostatic pressure at the bottom of the well and allowing reservoir pressure to lift the oil to the surface. Gas lift handles sand, gas, and deviated wells well, but it requires a high-pressure gas source, which is not always available. Rod pump, beam pump / sucker rod pump. The classic nodding donkey, a walking beam at the surface driving a string of sucker rods that connect to a downhole plunger pump. Simple, reliable, low cost, but depth limited to perhaps 8,000 barrels per day. Unsuited for deep or high-rate wells, ideal for mature onshore fields producing at low rates over long lives. Progressing cavity pump, PCP, a helical rotor turning inside a stator, essentially a downhole version of the Archimedes screw. It handles heavy, viscous oil and high sand production far better than an ESP, used extensively in Canada's heavy oil fields and in wells where sand production is a persistent problem. Every reservoir eventually depletes, pressure declines, the gas fraction drops, the water cut rises. The natural energy that once drove oil to the surface under its own pressure is no longer sufficient. When that happens, and it always happens, the well needs help. That help is artificial lift. More than 90% of the world's producing oil wells use some form of artificial lift. The choice of lift system is one of the most consequential decisions in the production engineering lifecycle. Select the wrong system and you commit to years of high operating costs, frequent failures, and lost production. Select the right system and the well produces reliably for a decade. The electrical submersible pump, the ESP, is the workhorse of high-rate wells. In the Middle East, in deep water, in any field where individual wells produce multiple thousands of barrels per day, the ESP is almost certainly the lift system of choice, but ESPs fail. On average, an ESP in a challenging environment, high temperature, high gas fraction, abrasive solids, runs for 2 to 4 years before failure. When it fails, you mobilize a workover rig, pull the entire tubing string, replace the pump and motor, and run it all back into the well. The cost, in direct intervention expense and in lost production, can run into millions of dollars per event. The industry has invested enormous resources into extending ESP run life. Every additional year of run life saves millions of dollars per well. The animation follows the oil through the LACT. First, a strainer to remove any remaining solids. Then the meter, typically a positive displacement meter or a Coriolis mass flow meter, accurate to within 0.25%. An automatic sampler extracts a representative sample of the flowing stream, a few milliliters per barrel accumulated over the batch, for laboratory analysis of API gravity, sulfur content, and BS&W. If the BS&W exceeds the pipeline specification, typically 0.5%, the LACT diverts the oil back to the treating system rather than allowing it into the export pipeline. The custody transfer meter is the final arbiter. It is the point at which ownership of the oil transfers from the producer to the pipeline operator or the buyer. Every barrel is measured. Every measurement is auditable. The accuracy and reliability of the metering system is not a technical detail. It is a commercial imperative. A 0.5% error on a field producing 100,000 barrels per day at $80 per barrel is worth $40,000 per day. Over a year, that is nearly $15 million. Metering disputes between producers, pipeline operators, and government regulators have ended in litigation, costing hundreds of millions. From the LACT unit, the oil enters the export pipeline, or for offshore fields without a pipeline connection, it is stored in the hull of a floating production, storage, and offloading vessel, an FPSO, and periodically offloaded to a shuttle tanker. And the offshore route, an FPSO, a converted oil tanker with processing equipment on its deck, permanently moored above the field. Oil flows from the subsea wells to the FPSO, is processed on board, and is stored in the vessel's cargo tanks. Every few days, a shuttle tanker arrives, connects to the FPSO's offloading system, and takes on a cargo of perhaps 500,000 to 1,000,000 barrels. The shuttle tanker then delivers the crude to a refinery or a transshipment terminal. For a deepwater field far from shore, the FPSO is the only economically viable export solution, and take years to permit and construct. Station within months of the development decision. It processes, stores, and offloads, all from a single floating facility. When the field is depleted, the FPSO can be disconnected, towed to a new field, and reconnected, an asset that moves with the opportunity. Cut 2. Episode 7 Preview Imagery. Crude oil being heated in a furnace, rising through a distillation column, separating into fractions. Light gases at the top, naphtha, kerosene, diesel, gas oil, and atmospheric residue at the bottom. A catalytic cracker, a towering vessel where heavy gas oil is broken into lighter, more valuable products. A reformer turning naphtha into high-octane gasoline components. The oil is out of the ground. It has been separated, treated, measured, and exported. It has traveled through pipelines or across oceans in tankers. Now it arrives at its destination, the refinery. That is the subject of Episode 7, Inside the Refinery, Cracking, Distilling, and Transforming Crude. The crude distillation unit, the first and largest processing step, the atmospheric and vacuum towers, heat, vaporization, condensation, separating crude into boiling point fractions. The conversion units, catalytic cracking, hydrocracking, coking, breaking heavy molecules into lighter, more valuable products. The treatment units, hydrotreating, sulfur recovery, removing contaminants and meeting environmental specifications. And the blending and product dispatch, how a barrel of crude becomes gasoline, diesel, jet fuel, heating oil, and the petrochemical feedstocks that underpin the modern economy. This is Crude, a SeaMayors documentary series. Episode 7, Inside the Refinery, Cracking, Distilling, and Transforming Crude, next week. If this series is helping you understand how the industry actually works, from reservoir rock to refinery gate, subscribe and turn on notifications. And for the production engineers, flow assurance specialists, and operations personnel watching, drop your worst flow assurance story in the comments. The hydrate plug that took 3 weeks to clear, the ESP that failed after 6 months, the asphaltene problem nobody predicted. This industry runs on shared experience. Let's hear yours.